Okay, let's these look like slightly scary pens, but let's see what happens. Uh, I'm going to try to talk about two of my favorite things at the same time. I don't know whether I'll succeed or not, um, but I want to tell you about the way I cook up typing rules. Um, it's uh, Uh, it's a bit non-standard, but it has advantages to it. Um, and I want, um, by way of example, to talk about a compositional approach to type checking things which I don't expect you to know about unless you've been around for a while, that I call thinnings. So I'm notorious, everything reminds me of thinnings. Uh, so, so here goes. Um, right. Um, so I want to tell you. So I mean, imagine my surprise uh, reading somebody's PhD thesis in order to examine it. I turn the page from the end of chapter 3 and I see chapter 4 entitled McBride's Discipline. And I just laughed because my late father would have found that hilarious. I mean, just the idea that I might have some. And, but turns out I do. So, we write, um, uh, we build type systems by as inductively defined systems of things called judgments. That's the particular kind of formula we write in a type system. Uh, and a judgment might look something like um, I tend to write things like T admits little t. So big T might be a type and little t might be a term. And, and I'm a strange person who thinks types come first. So I steal the set theorist's symbol and write it backwards because it's reassuringly asymmetrical, at least in the dimension I care about. And uh, okay, so so the point is that there's some punctuation, and then there's some actual signals. Um, and the way I look at these things, every signal comes from somewhere and goes somewhere. It has a sender. Every signal has a sender. Um, and moreover, um, uh, every signal has a this somebody's going to make some sort of promise about the signal. And the person who makes the promise about the signal is called the guarantor. So every signal has a sender and a guarantor. And if the sender and the guarantor are the same person or the same agent, that signal is called a citizen. And if you're, so some of them are inputs, some of them are outputs. We'll get to what's going on in a moment. But crucially, if the person who sends a signal is making a promise about it, it's a citizen. Whereas there are situations where it is the receiver of the signal who is expected to make a promise about it. In which case, that signal is called a subject. So there's a distinction between citizens and subjects, which, as you might expect from being in the UK, subjects are the ones that get duffed up by the cops. and citizens are kind of trusted. And so, for example, when I say big T accepts little t, I'm going to say that big T is an input, and I'm actually going to write in curly braces to the left, like it's a Hoare triple, the precondition that says what it is we trust about the input. So there's going to be another judgment which says things are types. So what this means is you should not even ask whether big T accepts little t unless you are in a position to guarantee that big T is a type. The person you're asking to check this can trust you that big T is a type. But the person you're asking to check this is getting no promises about little t. Little t, so this is an input. This is a subject. Right. We're asking about this because we're hoping we're going to get a promise that little t makes sense. But it's reasonable to ask the question without making that promise. I mean, it's the reason, that's the reason we're interested in the question in the first place, is to find out whether little t makes sense. Yes?
What specific thing do we consider sender or receiver?
Well, so in particular, we'll formulate the idea that typing rules are basically things which get given, if you think of the judgment as a query to be checked, and then the typing thing to be checked is checked by making queries about subformulae. So in a typing derivation, the conclusion is being received and the premises are being sent. Okay, so there will be another judgment form because I live I split the world into syntactic forms which we check and syntactic forms for which we synthesize types. So there will also be a typing judgment which so this is subject and this is an output. Okay, so that's to say whoever it is says you can synthesize type S for E is their job to guarantee that big S is genuinely a type. So again, whoever asks us to synthesize the type of E is making us no promises about E. But once we are happy, we're making a promise about E and we're saying something about it, we're providing some useful information, and we're promising this thing is a type. Yes? So inputs and outputs are two kinds of citizen. So just depending on whether they're coming or going. Okay, so that's fun stuff. Let's write down a not entirely unusual typing rule. And what we'll find is, so when I write down a typing rule, the conclusion goes under a line and the premises go above it. This is standard issue natural deduction. There's nothing else standard about what I'm about to do. Right. So I'm going to say, can we synthesize a type for an application? By way of example. Right. First thing you'll notice, this is a subject. It's in the conclusion of a rule, which means we're receiving this. We're receiving a query. What's the type of f of s? For stuff we receive, we are allowed to take it apart only by a kind of pattern matching. So there's a separate notion of pattern from notion of expression. And this is in a position where where we're restricted to using patterns. That's to say, we're taking stuff apart, and there's only a few sensible ways of doing that. Okay, so next thing that happens, how do we synthesize a type for an application? Well, we start by synthesizing the type for the function. So we're now sending this f off as a query to say, what's the type of f? So this is an expression position. Right. When you're sending something, you're sending something denoted by an expression. When you receive something, you take it apart using a pattern. So what this means is that every schematic variable in the rule has a binding site in a pattern and various use sites in expressions. So this is highly non-standard. Most of the time when people write rule systems like this down, they expect all of the schematic variables to be systematically and silently universally quantified externally to the rule. Whereas here I'm saying, here's the actual binding site of f and s. Okay, so we synthesize the type of f, and back comes something which we're guaranteed is a type, and we're allowed to pattern match on that type to find out what it is. So I'm going to say it's some dependent function type, which looks like this. So here I'm saying, I've got my type back, and I'm checking that it matches this thing. Okay, so now I'm in a position, now that I've got so this is a pattern, and I've got, because outputs in rule premises are patterns. They come from somewhere, you take them apart. Okay, so now I need to check that little s is a valid input to this function f. So I check, does big S accept little s? So once again, what happens here, you got to think precondition, postcondition, right? Somebody made me a promise that this was a type, and I took it apart as a function type, which means that each of the pieces is a type. So I know the big S is a type. So I'm keeping my promise that I'm sending something which really is a type to check little s. Okay? Yep.
Would you have done this the other way? The way is probably the chunk with your instance, and then use that to construct.
No. Right. Not in dependency land. Right. And then, so finally, I give back, well, okay, so one thing also, here's the magic thing. You'll notice that every component of the subject in the conclusion is used exactly once as a subject in a premise. And the point is that having been validated by a judgment turns a subject into a citizen. So we are now allowed to use little s, and I'm going to use little s because I'm going to construct the type t with s substituted for the variable which is clearly bound in t, so I don't have to say what it is. Now, things that are important. We knew that big T was a type with a hypothetical x. And in fact, I'm going to say T with little s of type big S goes there. I'll have a rule for this in a moment. But yes, we've checked that little s has type big S, so it's all right to substitute little s with a type annotation for the variable. And that relies then crucially on the property that the whole system is stable under substitution, right? If t with a variable x in it forms a type, and I substitute something the right type, I still have a type. Right. Now, lots of people work really hard to prove that type systems are stable under substitution. But I work really hard not to prove that type systems are stable under substitution, because I make sure that the way I build them forces that to be true without any external assistance. So hooray, a thing we don't prove anymore. It's, you know, we've moved stability under substitution from the box of things that are hard to prove into the box labeled things that are easy to not fuck up. And the trick for making sure systems are stable under substitution is never to talk about free variables, right? Because what do substitutions act on? Free variables. So if you never say anything about free variables, you can't make a statement which is falsified by the action of a substitution. That's simple. Okay, figuring out how to never talk about. So you notice I don't have any context here. That's me not talking about free variables. Right. Okay, so that's an example of a rule. Yeah. So likewise in the rules, I only ever talk about context extensions, not contexts. So for example, I might say, we've had application, let's have lambda. Oh, there was one more thing I was going to say before I move on. Notice that this here substitution is in an expression position. And it's important that substitutions like this happen only in expressions, because substitution is very hard to do backwards. Right? You know, if we were allowed substitutions in pattern positions, we'd basically be asking for something psychic, something magical. So no magical thinking, substitutions only in expressions. So yes.
How do you determine which positions are expression and pattern positions?
Could you repeat the question?
So the question is, how do you know which ones are patterns, which are expressions? I'll draw my table. So we've got input, subject, output, premises, conclusions. Okay? So should be pat. Right. So if you were the rule, somebody's asking you about this conclusion, they're going to send you an inputs and subjects, and you take them apart with patterns. Then you're going to do some interaction. The premises are going to send off some subqueries. So the things that the premise sends, the inputs and subjects, are, well, the input's an expression. The subject is a variable which occurs in the subject of the conclusion. And then once the premise reports back some outputs, we take those apart with patterns. And eventually, when we've got enough information, we choose the expression that stands for the outputs we're going to give back. So, and information more or less flows, well, it has to be causal. Right. So there's another thing to say here. So this S is the citizen version of this S, now that it's been checked. And so secretly, what being a citizen means is having a semantics, right? Whereas this is just a lump of syntax that we don't trust yet. And now that we trust it, it has a semantics. So yeah, I'm going to give an example. I'm going to write the lambda rule as an example of a rule which which has a local context extension, just to show that happening. Okay, you see I don't have a type annotation on the lambda. I do know the type. I'm promised that this is a type. And correspondingly that big S is a type. So I can make a local context extension and check big T is in little t, or accepts little t, and that's it. I don't have to revalidate. I'm promised that big T is a type in the presence of some little x in big S, so I'm keeping my promise that this has to be a type. I'm checking little t. There's nothing else going on. So that's the rule for lambda. I will write down the two rules that are important if I'm checking. So I write a little underline to embed synthesizable terms into the checkable world. So if I'm checking something synthesizable, I synthesize it, and then I check that the type I want. This is clearly directed, and you can replace this equality relation with a subtyping relation if you're sufficiently not afraid of subtyping. But the thing about subtyping is that if you're not afraid of subtyping, you don't understand it. And that doesn't mean never do it. That just means you better know what you're doing. Okay, and then the other rule that allows it to change direction the other way. There's no magic, right? You can't just make types up out of nothing. So if you want to synthesize a type for something checkable, it better have a type annotation. And then you check, first of all, that the type annotation really is a type. And once you've done that, you're allowed to check that the actual term has the type in the annotation. And when you're done with that, now you can give back the type you first thought of. Okay. So that's input, subject, output as a way of working. One thing you notice is that one of the things about citizenship is that nothing ever moves from citizen to subject. Once your bona fides are established, you're trusted. And what this means is that the subjects of premises are subformulae of the subject in conclusions. And this makes it relatively straightforward to state a sensible formulation of type preservation where your proof by induction is actually going to go through. There are lots of type theories where the meta theory is made vastly complicated by constantly revalidating the context or something like that. Whereas here we do no such revalidation. Rather, we bookkeep who's supposed to be in charge of making what happen. Right. So lots of type theorists like to, for example, to make it admissible that if a type checks something, then it is a type. Right. That you can deduce the validity of the type from the typing derivation for the term. That causes lots of rules to have masses of bureaucratic extra premises to keep that admissible. Whereas here I'm basically saying garbage in, garbage out. If if I say big T accepts little t, and you execute little t, and it screws up because big T wasn't a type, that's on you, not on me. Okay, so high-level message. Stick with this discipline. Stability under substitution is no problem at all. And type preservation basically boils down to just checking the computation rules. are sensible. All the structural aspects of type preservation just work. I could talk about type preservation a bit more, but I don't want to. I want instead to talk about thinnings. And which way am I going to do them today? They're going to be like this. I might want some colors. So what even are thinnings? They're ways of talking about there are ways of talking about well, in one direction, extra things. In another direction, selections from things. So so here's a sequence with 5 things in it. Here's a sequence with only 2 things in it. And if I draw a line which goes like that, then what I'm saying is that I can make the big sequence from the small sequence by kind of diluting it with extra stuff. That's why they're called thinnings. But a thinning is viewed down the way. So dually, it's a selection. And thinnings behave an awful lot like binomial coefficients. And that's not an accident. This is just basically Pascal's triangle turned into types. Right? Yeah. Okay. And of course, if you select, if you don't make any insertions, or down the way, if you select all the things, then you get the identity thinning. And of course, thinnings compose. So I could have a thinning that that embeds just the red one into this 2-element list. And all I do is I stick them together spatially, and they compose nicely to get the thing which inserts all 4 of these extra things to get this 5-element list from this singleton. Okay? Yeah, it's so it's order preserving injections are what we have here. So we don't jumble things around. And of course, as well as having a composition structure, you can just paste these things together side by side. So if you've got if you've got 2 lists that's thin, you can concatenate. So what that essentially means is, if you like these words, that thinnings are a very particular monoidal category. In particular, they're the monoidal category generated by the ability to insert a singleton. You know, that's your lot. What's interesting is how you type check these things in a sensible way. Because I'm going to tell my usual story that there are 3 ways people talk about categories. I mean, there are more than 3 ways people talk about categories, but in particular, there's set theorists talk about category like the jigsaw pieces which look like this. So there's like each piece has a lug at both ends, right? That's to say, they say there's a set of morphisms and there's a map called domain that maps morphisms to objects, and another map called codomain that maps morphisms to objects. So that's essentially you read off source and target from the morphism, right? But you'll notice I'm using for category theorists that these jigsaw pieces don't compose. Yeah. So that's to say, if you want to say what an identity arrow is, the identity arrow needs to carry its object explicitly so that the domain and codomain maps can read it off. Meanwhile, for composition, you have to do a coherence check, which amounts to the bit of an adapter that's going to plug in the middle between two of these pieces. So let's point type theorists smugly turn up and say, no, 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 you want to say, given a source and target object, what the morphisms are. And the type theorists build pieces that look like this. And they don't compose either. In fact, it's hilarious. Now, you have a coherence check if you want to create an identity map, right? Somebody's going to give you two objects, but you can only have an identity morphism if they're the same. So that's where the coherence goes. Meanwhile, you can't check a composition because you don't know what's in the middle. So your bullet or your semicolon needs to have an object annotation on it unless you're resorting to magic. And it's noticeable that these are practices done by people who are just casual about magic. But if you work with computers, you can't afford to be casual about magic. So, so if you're Estonian, you build categories out of pieces that look like that. And they bloody well do compose. I'm going to tell a similar story about thinnings, but I'm going to warm up first with just a little bit of stuff about lists. So I'm going to have a judgment which is going to assume that there are that list X accepts two things, and then I'm going to have oh yes, and so this is list subtraction, which doesn't always hold. You can't always do, but this judgment asserts that Y's is a suffix of Z's, and it outputs the prefix. So we can see if we can write down a system of rules for this sort of thing in input, subject, output style. So if somebody gives me Z's and they want to subtract nil, then I'm entitled to give Z's back without any further checking. And whoever promised me that Z's was a list, I say thanks very much. I will pass your promise on to my customer. Okay. Then there will be a rule which says Z's append singleton Z, take away singleton Y. I have to check that big X accepts that Z and Y match. And if that's the case, I give back Z's. And then if I have Z's take away Y's prime append Y's, what do? I say, I check that Y's is a suffix of Z's, and that gives me Z's prime. And then I check that Z's prime has a suffix Y's prime, and that gives me X's. And now I can give back X's. Okay. You'll notice that this is not a cons-based presentation of lists. This is lists built by concatenation from singletons. That's to say, it's taking seriously the monoidal structure of lists, and none of this sort of business has a cat in hell's chance of working unless your type theory understands the equational theory of monoids. So believe me, that's actually one of the more straightforward tricks to play to get those things to hold. So it's kind of embarrassing that in 50 years of Martin left type theory, append is only associative when you kick it. That's just embarrassing. Yes. So let's fix it. Okay. So I want to talk. So this is going to be useful. When?
Should I be confused about Z equals Y living in the type X?
Well, I should probably write a few more administrative things down. There should probably be an element type annotation in this judgment somewhere. So I'm doing a bit of magic. This judgment should really be should really have some kind of bracket containing the type X, and I should be adding that X has to be a type, and I'm being sloppy. Okay, I'm going to erase this picture and rearrange it.
Equality on them?
Yes. And in particular, the equality for lists includes the monoid laws. Okay, so I don't have much time. I might have to do thinning with a bit of just jumping straight to the answer. Okay, so what happens? I'm type checking a thinning, which I'm going to write. Oh, this eraser is terrible. I'm going to write this thing as X's is included in Y's, and I should really give the element type here. I'll probably forget about the element type. Right. So how do you check a thinning, which I will always write as theta? Well, so the trick is that I don't use this type checking judgment to check thinnings. I do the Estonian thing. I forget temporarily that I know both ends of the thinning and just hold on to the big end. So I'm going to draw a picture like this. So here's my thinning. And I say, I'm going to tell you a list which I hope the big end of theta is a suffix of. So I'm going to tell you like more stuff, the stuff you're choosing from and more. And then you're going to give me back what I call the leftovers, and that's why, because they're on the left and they're over. So this is an output now, x's. No, I shouldn't say x's. I'm going to say l's. But we're also going to get the Rightunders. That's to say, the things that were not only not we didn't just look at them, we actually decided to keep some of them. So that's going to be the r's here. And then you have to check to interface between these two judgments. The l's is nil and the r's is x's. But now we can define this thing inductively, and it will behave in a pleasingly compositional manner. Right. So we start off with, I get to draw pictures. We start off with z's accepts all y's. So all says keep all of these ones. We have to check that list x, and again that x should be knocking around somewhere. List x accepts y's, and we also have to check that z's minus y's equals x's, and now we say that x's are the leftovers and y's are the Rightunders. Okay, then there's a very similar thing which I will actually, we will draw it. So there's a thinning which looks like, it's called none y's. And it looks like that. I've messed up. This whole thing is z's on the top. And again, I'm checking list x accepts y's, and I'm checking z's minus y's is x's. X's are the leftovers, and the Rightunders are nil. Yes. Okay, so we've got, this is basically the identity, and it does require an annotation. We don't, because we're not going to get away with the whole story entirely. See what's gone wrong with this eraser. It's actually bald. Right. So let's do tensor. Yes?
So what you're doing here is basically having a separation logic to make sure that the thinnings will fit nicely over there.
Yeah.
All right.
Yeah, so for tensor, so that's to say you've got thinnings which are side by side, theta, phi. Well, it's not going to be a big surprise, is it? That we're trying to fit them into z's, you say, here's my typing rule. You start with Z's, you check theta, outcome x is 1 and z prime. Then you feed z's prime in and you look for phi, and outcome x is 0 and y's. And then you give back x is 0, append x is 1, and y's. Okay, fine. And finally, composition. So here's z's again. What do? You hang theta off z's, out comes z's prime, and picking random things and x's. Then off x's, you hang phi, and out comes y's, say. And here, you insist that the leftovers are nil. And now you can give back z's prime as the leftovers and y's as the right-unders. And again, you'll notice, for example, that for the invariants to hold on these things, we actually need the monoid laws to be just true. So yeah, so here's the thing that input, subject, output isn't just for the type checking, type synthesis. It actually pays dividends to have bespoke judgments still under the input, subject, output discipline for specific constructions. So that's what's happening here, is that it interfaces at the top level with typing, but it gives us a compositional checking for thinnings as we go along. We play very similar games in all sorts of ways. This is one of the things I do with Continuum, is that our brat programming language is basically, how would you invent functional programming again if monoidal structure was more important to you than functions? And there's, yeah, Georgi will do the same trick, bigger with matrices. What can I do for you?
So I don't know if if this is correct, but it sounds like moving to like the Estonian way of looking at things. It's like we're going to the slice category to some extent.
Yeah, so it's the Estonian way is my version of the slogan is index over the past, fiber over the future.
And the other question is so the like vertical and horizontal composition correspond to the two different types of coverings in the thinnings paper. Is that correct?
No, not really. No.
This kind of looks like a partition, right? And then the other one looks like, you're exhausting all of the stuff in the thing.
Well, I mean, it so happens that every you can manufacture partitions this way, but partitions don't have to be contiguous, whereas tensor is contiguous.
I guess my other question is, you said tensor here, and I was just, I guess, because is there another kind of product, or is that, because I don't know. It's interesting. It seems like there's two kinds of
Right. So what I'm doing to the objects here is just list concatenation. And so list concatenation lifts to essentially thinning concatenation. I mean, secretly, a thinning is a bit vector, and we know which things we're selecting from, but then there are some bits doing some selection. So what we're doing here is concatenating bit vectors, and what's happening here is that we're substituting the elements in one bit vector for the ones in another. So those are perfectly sensible operations. And then this thing is the bit vector that's all ones, the full bit vector, and this is the one that's all zeros, the empty bit vector.
At some point there, you said something related to these deduction systems or some types of thing that not talking about context. And there's lots of variables on the board right now,
but they're schematic variables. I mean, so there's it's always important to distinguish the variables that live in the object language, the language we're talking about, like the x's that get bound with the lambda and the x in the pi type. Those are object level variables, and they are essentially first order things. Meanwhile, there's a different variety of variable which we use to name the places in a judgment that we're talking about, name the things that are there. So that's to say, they live in logical meta language that's talking about the type system. So I'm not really talking about a literal program variable y's here. This is any old list. So the things that behave in that meta way, those are the things that are bound in patterns and used in expressions. And they are also second order. So that's to say, for every one of these meta variables, there's a collection of object variables that it's allowed to depend on. Although we see none of that, there's no binding going on in thinning land. Absolutely.
point out which of these schematic variables on the board are use sites versus whiteboards.
So here, I mean, it's this thing still holds.
I didn't.
Right. Okay. So that's to say, if you imagine you are the implementation of a typing rule, then someone's going to ask you to solve a type checking problem for you. They're going to send you some inputs and some subjects, and you're going to take them apart. You're going to look at them. And that means that's where you use patterns, and that's where schematic variables get bound. And then you are going to trigger a bunch of subqueries for the premises of the rules. So you will choose to send some inputs and subjects. So the inputs can be expressions. The subjects have to be subformulae of the subject that you were sent. And then you will get back from the queries you send some useful outputs, and you take them apart with patterns. And then finally, you choose the expression to send as your output. So here, for thinnings, the subject are the thinnings themselves. The inputs are the big list that we start with. And the outputs, plural, are the leftovers and the Rightunders. So here we're really saying, so of course, you're allowed to pattern match on outputs. So here I'm allowed to say, I demand this one is nil. Yeah, so that gives us a compositional story. And the same sort of thing has been known about for a while, like people doing type checking linear languages using the leftovers method. So that's to say, instead of saying the stuff that's in the context has to all be used up, you do that at the outer level. You say because then when you're type checking something which is a linear pair, you need to say, well, some of the resources go left and some of the resources go right. But you know, the rule for constructing a pair doesn't know itself who wants what. So the business of magically chopping up the resources is not algorithmically feasible. So instead, what you do is you say, well, you know, you can have all of these things, but you know, I'll see what you give me back and not that you don't use. So so you do exactly this direction flipping trick, and of course, as people who do category theory by means of type theory, we exactly spend our time doing index to fiber flips in both directions in order to avoid pesky time travel, which is regrettably impossible. And right, you know, so the alternative for humans is what we call proof by intimidation, where you just leave stuff out and don't bother doing the coherence checks, and you expect somebody less important than you to do all of that shit. Well, the trouble with computers is that they're too stupid to be intimidated. So you actually have to figure out how to make it work. So,